And now for today's program, we have Petr Laštovička, who's going to talk about NAC-colorings, complexity, and algorithms. It's a rigidity theory.
Okay, thank you for the introduction. So yeah, today I'm going to talk about my bachelor thesis that I did with a collaboration with my supervisor Jan Legersky. We continued on our paper written during VLAT summer school here at FIT CTU. In the talk, I'll first introduce you to rigidity theory. Then I'm going to talk about the proof that NAC-coloring existence is also NP-complete on graphs with degree at maximum degree 5. Then I'm going to talk about FPT algorithm parametrized by treewidth that I made, and lastly about the algorithm that we designed, implemented, and evaluated for heuristical NAC-coloring search. So first, rigidity theory. Rigidity theory is a branch of combinatorics and discrete mathematics related to objects with joints and rigid bars, so graphs. The base element is a derealization, which is a mapping of a graph into a d-dimensional space, and a framework which is spare of a graph and such a mapping. What's important for us is the definition of non-trivial flex. You can either read this definition, or simply it means that you take a graph, you project it into a d-dimensional space, and then you move the vertices while not changing the lengths of edges. So if you can do such a continuous transformation, then you got a non-trivial flex. And if you're able to find such a non-trivial flex, or if the realization you have has such a flex, then we are talking about a flexible realization. What's kind of paradoxical about this is that for a graph, either almost all of the realizations are flexible, or almost all of them are rigid, which means they are not flexible. What's paradoxical is that the almost all. For example, here you can see a free prism graph. If you realize it, if you take this realization, you can clearly see that you cannot move the vertices without changing the edge lengths. These middle ones just won't allow you to do it. But if you take this realization of the same graph, suddenly you are free to rotate these two triangles however you want. So this is a flexible realization, this is a rigid one. Yeah, with that, I will move to NAC-colorings. NAC-coloring is a red-blue coloring such that, edge coloring, sorry, such that there is no almost cycle in the graph. What's an almost cycle? Almost cycle is a cycle where all the edges except for one have the same color. So like all are red, for example, and one is blue. So we want to avoid such cycles in our graph. Also, we want the coloring to be surjective, so both the colors are used. We cannot just color the graph with red. That would be too simple. We can check in polynomial time whether coloring is a NAC-coloring by finding red connected components and blue connected components. And if there is for example, a red edge that's incident to two vertices in the same blue connected component, we can easily see that there's an almost cycle. Draw it. If there's a blue edge and then a red component, then we know that there's an almost path going through the red component with one blue edge. So like with this simple fast polynomial check, we can check for the coloring. That will come useful later. What's useful for us now is this theorem that for a connected graph G with at least one edge and a flexible quasi-injective two-dimensional realization, so a graph has such a realization only if it has a NAC-coloring. So yeah, we are gonna stick with just 2 dimensions for the rest of this talk. Quasi-injective means that no two neighboring vertices are mapped to the same location. So like non-neighboring vertices can be, only non-neighboring cannot. for injective, it remains an open problem. That's for future. And what this gives us is some combinatorial way to see if a graph has flexible realization or if it has not. So like again, for free prism, you would think that, hey, it's rigid, there's no way to do it, but we found a NAC-coloring, and from the NAC-coloring, we can map to a flexible realization. Similarly, for this six pentagon thing. Sorry?
It's K3.
Yeah, that's it. Sorry, I don't know name of geometry objects in English that well. So yeah, for the existence questions of a NAC-coloring, it was shown before that it is NP-complete to decide whether a graph has a NAC-coloring. There's a correspondence with a stable cut, which is independent set that's also a vertex cut. If there's one, there's also a NAC-coloring. As you can clearly see, it's NP-complete to decide whether a graph has a stable cut or not. There are also some polynomial checks. For example, if a graph has less than 2v-3 edges, then we know that it's flexible. Therefore, there's a flexible realization. Therefore, there's a NAC-coloring. And because of that, the question whether graphs with maximum degree 3 have a NAC-coloring is easily checkable and answerable, and therefore not NP-complete. What we are focused on is maximum degree 5. We based our proof on a reduction from FreeSat from a previous paper, where we, for a formula, create a graph gadgets that we combine together. I'll show them in a second. The original proof gives a no bound on the degree of vertices, and therefore we introduce a construction that's similar, but yeah, differs in the significant parts important for us. So yeah, we construct an auxiliary graph for a FreeSat formula. On it, we ensure that a literal and its negation give different values and that all the clauses are preserved. I'll show it here on the pictures. So let's start with a second gadget. Here we have some true part of the graph, false part of the graph, and then we have literal and its negation. Now, if the literal and its negation would be colored the same, consider that both would be blue, meaning true, then we have created an almost cycle here, and therefore it's not a NAC-coloring. Similarly for red. So from that, we know that xi and negation have to have different colors. With this gadget, we ensure that, similarly, that they have also different values. There's a thing with true and false and surjectivity that I missed here, but together with this gadget that also again ensures that they have different colors. For example, if they would be both false, you can see that red almost cycle would be created here again. So together with the surjectivity, from this we get that both colors are used and literal and its negation get different color. And the last gadget used for clauses, consider that neither of the literals in the clause are satisfied. Therefore, all the gray edges are red. Then we've created an almost cycle going here, and that's again not a NAC-coloring. So if we have a NAC-coloring, then at least one of them has to be blue, and we have satisfied our clause. Yeah. Also, we showed that the problem is NP. Oh yeah, sorry. And we made sure that all the vertices are maximum degree 5. And from that, we showed that it's NP-complete on graphs with maximum degree 5. And from that, we also showed that the problem is NP-complete on graphs with average degree 4 plus epsilon, while for maximum degree 4, the question remains an open problem, whether it's NP-complete or not. After this, I'm going to move to the FPT algorithm for NAC-coloring counting. First, we showed that the problem is fixed parameter traceable by treewidth using a mosaic second-order logic. We defined our problem and by Carle's theorem. Sorry, I'm not able to pronounce the name correctly. Courcelle theorem. There exists an FPT algorithm, but the complexity bound given by the theorem is quite high, so that's not something that we would like to see. Therefore, we designed our own algorithm parametrized by treewidth, used not only for existence but also for NAC-coloring counting. Note that in a nice tree decomposition that we use introduce edge nodes, meaning that when we introduce a vertex, we don't introduce the edges incident to the vertex. We introduce them later in a separate nodes. We also have a variant where it's introduced together, but for understanding, it's simpler to separate it. And on the tree decomposition, I define a dynamic programming algorithm. And for that, we want to have some sort of a state. So for each node in the tree decomposition, we take the back of vertices and take all the partitions on the back. And then for each partition, we take all the binary relations on the parts in the partition. I'll show a picture quite soon that will make it clearer. It's quite a huge state space, I know. So once again, I take the vertices in the back, create a partition from it, and for each partition, I create a relation on the parts. So either parts are neighboring or they are not neighboring for each of the parts. We are going to be counting almost NAC-coloring, which is the same as NAC-coloring, except for the surjectivity criteria. So we allow monochromatic colorings. And yeah, here I define how what it actually means for, or what's the correspondence between the NAC-colorings and the states that we're going to be using. So a state is consistent with almost NAC-coloring delta if for both halves. Oh, sorry, I skipped this, sorry. For a part and partition and related relation, we take such a pair for both red and for blue, and the four tuple of these four objects creates our state. And now for both the halves, let's say for the red one, two vertices are in the same part if they are in the same red connected component in the almost NAC-coloring delta, and there's a relation between parts of two vertices if there is a blue edge connecting these two parts, not necessarily in the back. It can be somewhere in the graph that we have already constructed somewhere before. So finally, for the pictures. There's an example of a state that states that the first vertex is in a red component of its own. These two vertices share a red component in some almost NAC-coloring, and this is also in a component of its own. Similar for blue, these two vertices share a common blue component, these share a common blue component. Here, this is how I reflect that between these two red components, there's a blue edge somewhere in the graph before. Maybe why is this important? In case a red edge is added here, then we've created an almost cycle with the blue edge here, which we want to avoid, so we keep track of these neighboring edges. Similarly, here there's a red edge somewhere between this red component and this red component. Also, the states can look like this when all the vertices are in the same component, and this can still represent some almost NAC-colorings. And with that, I can finally define a cache function that we are gonna show the formulas for. And yeah, it stores for each node in the decomposition tree and each state the number of almost neck colorings that are consistent with such a state. So like how many almost neck colorings are represented by the state, actually. So first, for a simple example, let's do introduce vertex node. Once again, we are not introducing edges. We only introduced the vertex. So this is what we had before. We've introduced this vertex. We know that for all almost neck colorings, this vertex has to be in a part of its own, as it's isolated. There are no edges. We haven't introduced them yet. So we can see that if we would forget this vertex, this represented some amount of almost neck colorings. So with the vertex added, this state has to represent the same amount of almost neck colorings as the previous one. So from that, we get a simple cache relation. These are the states that cannot represent any almost neck colorings, because here we state that there's a blue edge connecting this part with newly added part, but that cannot be true because we haven't added any edges. And here we state that the vertex is in the same part as already added vertices. That also cannot be true because we haven't added an edge. I showed it for the red half. It works the same for a blue half. And yeah, this is how it could be written. I'll spare you of this, but the most important part is, yeah, we just take the previous cache value, or we state that it's the same for the cases that I showed, or sorry, for the cases where the vertex is isolated. For the forget vertex nodes, either the vertex was in same part, same part, or same red component, if you will, as other vertices in the back, then we can just forget it, as the part in the vertex back still represents the vertex. Represents the vertex. And the other option is when the vertex was in a part of its own, then also like we don't care anymore, as we are adding edges to the vertex back or like somewhere further in the graph, and that cannot cause any new almost cycle. It's not already represented in the first part of the state. As if there would be an almost cycle, then it has to pass a blue edge into the part and then blue edge out of the part, which is not an almost cycle. Finally, for the most interesting node, the introduce edge node. Consider that we are introducing a red edge. And we'll consider only resulting states that actually like make sense, that can be consistent to any almost neck colorings. And therefore, I think the mistake that you found is not a mistake because we consider only the valid states, but we'll discuss it afterwards. So for the red half, if we added the red edge, what could have been the case? Either both the vertices were already in the same red part, which I try to represent here, or they were not in the same red part, and there was no blue edge connecting them. If so, then we just created almost cycle, so we don't care, we'll forbid that state. For the blue part, we've added a red edge between two blue parts. If not, then we've created an almost cycle, so they must have been in two different parts. And therefore, if we added edge, we have to represent the fact that there's a red edge connecting these two parts. And the edge could have been there before, as now we don't mind, we've created a cycle with two red edges, we don't care, or it could have not been there. That's like also fine, we've just like represented a newly added edge with the neighboring relation. So we have two options for red half, two options for blue part, 2 times 2 is 4. We get 4 states from the child node that represent some almost neck colorings, and by adding the edge, we extend these almost neck colorings. So we sum sum the numbers of neck colorings of these 4 previous states. And finally, for the join node, for simplicity, we can create the nice decomposition in such a way that there are no edges currently between these vertices in the back, which just simplifies our proofs. It would work also otherwise. And what we do, this is a state that comes from a left branch of the decomposition tree. This comes from the right branch of the decomposition tree, and we want to join these states, or the almost neck colorings represented by these states. Therefore, if this edge, this vertex was in the this red part, but in the other one it's in another red part, it joins the same red part, and now it can access the top one. I can't reach it there anymore. As we are joining the almost neck colorings on different subgraphs, then the red components simply merge. And now we can, through this component and this component, access this vertex. And therefore, all the vertices have to be in the same red component in this example. So it's like just squashes together, like union fine joins together. And if there was a blue edge connecting one of these smaller parts that got merged, there is still a blue edge that is neighboring the red component, even though it's larger now. So we have to preserve the property. And to evaluate a state, we take all the such states that merge into it. So to get value for this, we take all the pairs that merge to it. And for each of them, we sum the number of neck colorings here and neck colorings here, as we take a product of them. The states that are, for example, not valid is this one, as if we merge these 2 vertices into, or these 2 parts using this part, then we've created an almost cycle with blue edge that's somewhere here and goes through the other component. And it can also happen transitively, like here, that the almost blue path would look like this, traversing all the red components. So for these, we don't consider them, or the state they end up in is not valid, and we just assign 0. So we proved all the important nodes. I omitted a root and leaf node, sorry. With induction, the state space, as I said, is quite large. So the number of partitions per vertex base is bounded by k+1 to the power of k+1. And for each such partition, we have 2 to the power of k+1 choose 2 relations per each part, which creates quite a big state space that we have per node. Also, there are 2 halves, so that's squared. And together, when we combine all the complexities, the join node is the most complex one, we arise to this final complexity of the algorithm that's super exponential in k, but linear in graph size, or polynomial, linear in graph size. And for time reasons, I'll skip this slide quickly. So lastly, for the we only proved the FPT algorithm, we did not implement it. What's implemented is an algorithm for heuristic neck coloring search. So first note that if you have a neck coloring on a graph and you restrict it to a subgraph, then it's still almost neck coloring or a monochromatic coloring. You cannot create new cycles by taking a subgraph of a graph. That's what we... I'm mentioning the previous solution, which was just a naive one. Try all the colorings, remove the symmetric ones, and then use triangle connected components. Note that if you have a triangle and you would color 2 edges with a different color, then you've just created a normal cycle. So from that, it goes that all the triangles, all the edges of every triangle have to share the same color in every neck coloring. And we can use this fact to find triangle connected components that are components from triangles that are joined together. And we know that the whole component has to be colored the same way, which reduces our search space significantly. I improved upon this idea with these two cases. If there's a monochromatic class, this is what's my update of the triangle connected component. If you have a monochromatic class and an edge that connects it to vertices from the class, then the edge also has to be in the class. As if it would be blue in this case, an almost cycle is created. So we know that always it has to have the same color. In this example, if there are two edges like this for a monochromatic class, we know that they have to be in the same monochromatic component themselves, not the same as the previous one. But again, if there would be a red edge and a blue edge, then we've created an almost cycle. So they have to have the same color in every NAC-coloring. One optimization with using bit ends, bit operations instead of running the polynomial check. I'll skip this again. And yeah, so as I said, a NAC-coloring restricted to a subgraph is again a NAC-coloring or monochromatic coloring. So our strategy for algorithm was as follows. We took an input graph, decomposed it into subgraphs. We found almost NAC-colorings on the subgraphs, and then merged the subgraphs again to the original graph. The idea is that it's simple to find NAC-colorings on small subgraphs, and then if we merge them together, we cut through the state space and remove many of the options that we would have to otherwise check. So first, for the decomposition, we set a target for number of monochromatic classes per subgraph. Monochromatic classes are useful. We don't want to split them, so we created subgraphs from the monochromatic classes. The best performance was achieved with just a few, like 5 around monochromatic classes per subgraph. And the most performing strategies were either just take vertices on the input as they are, as some synthetically generated graphs are generated in a way that's just great and hard to reproduce. Or otherwise, we had an approach based on breadth first search with priority for cycles. So we are trying to find cycles and form the subgraphs from the cycles. As cycles can again remove some of the NAC-colorings sooner. And then for merging strategies, we've every time chosen 2 subgraphs and merged them and colorings on them. Everything was, of course, lazy with iterators, all the nice stuff. And the best performing strategies were either linear, where we took one graph and then slowly merged it with all the other graphs. So like if you're from functional world, then calling reduce on a list of the subgraphs, or shared vertices, where we tried to merge subgraphs that shared a lot of vertices with the goal that there will be also many cycles. What did not work very well was merging graphs in a tree-like manner. So let's say that we have subgraphs, then we would decide to first join the small ones and then join the larger ones. This worked for some graph classes as well as the other ones, but for other, this was terribly slow for some reason that we are not sure about. And then for benchmarks, first, there are different point of views how to look at the problems. So either there are graphs that have many NAC-colorings that have just few or that have none, and the performance difference for that. Also, it depends what your goal is. So you either want some NAC-coloring for the existence, you want all of them, or you just care about the number. For the number, the FPT algorithm would be possibly great, but as I said, it's not implemented yet. Eventually, maybe, who knows. So for graphs with many NAC-colorings, there's so many that it's really easy to find any of them, and even naive algorithm is fast enough. With the optimization, with the bit operations that I skipped before, it's even faster. But if you want to list all the NAC-colorings, not only find a single one, then from something like 15 vertices, my algorithm is already faster. And in every case, you can see that the number of polynomial checks decreased. The problem is that the additional energy or overhead is significant compared to the simplistic naive approach. Yeah, for some graphs, you can see that here the naive already starts to fly away around 16, 18 monochromatic classes in a graph. And this part of graph is cut off because it was taking ages to run the benchmarks, so I had to limit them. And yeah. Then for graphs with no or few NAC-colorings, the naive search was not feasible, mostly for graphs with no NAC-coloring, because it has to iterate through all the cases, as we can find sooner that there's none. For most of the cases, of course, you can give me some SAT formula, and it will also take me long. But actually, from the graphs that I tried to generate randomly, it was hard to find a case that's actually hard for the algorithm, as with the monochromatic classes worked so well that for the hard cases, often it happened. The hard cases are the rigid ones, usually, that they collapsed into a single or just few monochromatic classes that's simple to solve. So yeah, also some graphs from it. Here you can more clearly see that if you try to list all the NAC-colorings, the naive approach flies away real quick, while yeah, usually for a single one, if there was one, it was still manageable. And yeah, this is what I've already said, I think. So yeah, as I said, this was extension of our paper from VLAT summer school here at FitCTU that we are extending with the FPT algorithm now. The code was contributed to PyRigi, which is a project related to rigidity theory with many useful algorithms. If you want to join, I think Honza will love to see you there. And with that, thank you for your attention. I'm ready for questions and discussion.
So how about other parameters?
Open problem.
I mean, we looked at any and decided that it's good to start with period.
Yeah, we got a suggestion from Michal that, hey, actually this seems like something that would be simple to do like that. So we looked in it and designed the algorithm based on it. And yeah, this was my first, not introduction, but place where I met parametrized complexity. I think treewidth was enough for now. But if you have a suggestion for a parameter, feel free.
Other question. For degree 4, so would you say it's more likely that it's polynomial or NP-complete?
Huh. I would expect it's NP-complete, as the bound that I showed that's used for maximum degree 3. Honza and other are working really hard to shift it even by one vertex up. So I think shifting the whole maximum degree up will be even more complex than this, and therefore I would expect that.
Okay.
But
I would guess the other way around.
You can get whatever. Intuition.
Other questions? No, then let's thank the speaker again.